Hello and welcome back. This is going to be video number 3 from chapter 18. And in this video, I'm going to go over Friedelcraft's alkylation. In the next video, number 4, I'll do Friedelcraft's acylation. So these are the learning objectives. And after you finish video number 4, you should be able to get through these. In these problems from the chapter 18 problem set, this also includes some of the reductions that I mentioned in a previous video. Okay, let's go ahead and get started with Friedelcraft's alkylation. So this reaction was discovered a long time ago, back in 1877 by Friedel-Crafts. And just like the name sounds, so we have this word alkylation. This means that we're putting an alkyl group on a benzene ring. Okay, and in this reaction, even though it's really old, this is still used today in the organic chemistry settings. And we've got a couple of different ways to do this. The most common way is using an alkyl halide. An alkyl chloride is what we're using here. And the catalyst for this reaction is aluminum chloride. And remember, I mentioned, I think in the previous video, that we see these metal salts. These are really good Lewis acids. So they can accept a pair of electrons. And we're going to rip off the chlorine here and make a bond from this carbon to the benzene ring. Okay, the inorganic byproduct that is formed in this reaction is HCl. So this alkyl halide is not a strong enough electrophile in this reaction, so we need the catalyst to make this more electrophilic by converting this into a carbocation. So just a reminder, we're talking about electrophilic aromatic substitution. So our reagent that's reacting with the benzene ring needs to be an electrophile. So the way that we generate the electrophile in this reaction using the aluminum trichloride, so we see a pair of electrons going from the halide to the aluminum to form this complex here. And we quickly break this bond to make a carbocation. So this here, in this reaction, this is our electrophile. And remember that the benzene ring here is serving as the nucleophile. Okay, so let's take a look at the mechanism for the reaction. So we have here our electrophile, right? Our carbocation, and in Friedel-Crafts alkylation, that electrophile is always going to be a carbocation. Okay, so again, the benzene ring here is serving as the nucleophile. It's going to attack the electrophile. Okay, and we will see that our intermediate is not aromatic, right? And then in the next step, going from, and again, we notice that we have an arenium ion intermediate that is resonance stabilized, right? So now we have, in the last step here, we're going to break the chlorine aluminum bond. We're going to do that so that we can deprotonate this site of the ring here to restore aromaticity. Okay, so once again, the product here is aromatic. So here's our organic product. This is the inorganic byproduct. Okay, so we can, instead of using an alkyl halide, we could also use an alkene, since we know that those are under acidic conditions. Those can easily form a carbocation. So here's another example of a Friedelcraft alkylation, but this time done with an alkene. And again, we're doing this in acid so that we make a carbocation. So in this mechanism here, so remember that this is a strong acid. So I'm just going to go ahead and write H+ up here. So here we have the electrons from the pi bond attacking a proton from the acid, and let's draw our carbocation that's going to serve as our electrophile. So here, this is going to follow Markovnikov's rule, right? So we expect the hydrogen to add here and the carbocation to be here. So our plus, we've broken the pi bond. So here is our electrophile, and it's going to react with our benzene ring. Okay, let's make it a benzene ring instead of just a cyclohexane ring. All right, so we see that attack there. And then what do we expect? An rhenium ion intermediate? You betcha. Okay, I'll put my plus charge here. So there's one hydrogen here, there's one hydrogen here, in addition to our CH3. Okay. All right. And then I think it's helpful to see that hydrogen. So in the last step, we can go ahead and, rip that off. And keep in mind, and you can draw, of course, the other, I'll let you do that, the other resonance hybrids. You should practice drawing those here. And then we're going to deprotonate here. If you want to use the conjugate base of this, or you could just use water also, that's fine. But we're going to deprotonate, and then we get this as our major organic product. So this is great, but Friedelcrafts does have some limitations, the alkylation reaction. The first one, since we're making a carbocation, that's our electrophile, rearrangements are possible. We can see hydride shifts and we can see methide shifts. So for example, here, you might think that we would expect to get this as our product. 1, 2, 3, 4. 1, 2, 3, 4. You would expect to get this as your organic product, but instead what's going to happen is you're going to see a rearrangement where you have, in this case, a hydride shift. So let me just draw, what is the carbocation that initially we make here? I should keep this in red. So we're going to make CH3, CH2. I'm drawing this funny for a reason. So this here is a primary carbocation, right? And if I do my hydride shift, I end up with, let's just put that here. So again, this is a hydride shift. And let's just make that arrow look a little nicer. And instead, if we do that, then we get a secondary, right, carbocation, which is more stable than a primary carbocation. So what we actually get way more of in our product is this. I'm gonna go ahead. And so again, reacting with our benzene in the presence of our catalyst, what we get instead, much more of compared to this, is this here. I'm gonna go ahead and draw this down just because I'm running out of room. Okay. All right, so rearrangements can happen in Friedelcraft's alkylation, so that can be problematic. It's helpful to just remind ourselves about carbocation stability. So primary carbocations are less stable. then secondary carbocations who are less stable, then tertiary carbocations who are less stable than allylic carbocations. Let's look at another example where we can see rearrangement occurring. So we imagine here, if we rip off the chlorine here, we get a primary carbocation. If we do a methide shift, then we end up with a tertiary carbocation, right? So that's what we're going to see happen. And that tertiary carbocation then is going to go on to react. Let's draw what we're going to make as our major product then. Our major organic product is going to, then be this. Okay. All right. So that's a really important limitation that you need to know about with regards to this reaction. One of the things this reaction, though, is really good for is making fused ring systems, but you still can get rearrangements. And so this reaction here is going to be an intramolecular Friedel-Crafts alkylation. I'm just going to write that down. Intra with an A, molecular Friedelcraft alkylation. Okay, so intramolecular reactions are reactions that happen within the molecule rather than in what we're used to seeing, like in the previous example, was an intermolecular reaction between molecules, right? Okay, so here we have a benzene ring with an alkyl halide on it. And let's go ahead and add in our catalyst, aluminum trichloride, right? And so in our first step where we are going to generate, we're going to make our electrophile, that's going to be our carbocation. This chlorine is getting ripped off. And here we've got a primary carbocation. If we do a hydride shift, then we can make a secondary carbocation, okay? And we know that 5-membered and 6-membered rings are super stable. And so I'm gonna go ahead and I've just wrapped this piece around after doing the hydride shift. And then I can have here at this position, a pair of electrons from the ring come out and form a bond to this carbon. So we have now a 5-membered ring here. So this is our rhenium ion intermediate. You should be able to draw, remember it's resonance stabilized, you should be able to draw 2 other resonance hybrids for that. And then we're going to restore aromaticity here by deprotonating the ring. And here is our major product. Notice it is a fused ring system. So this is a Friedel-Crafts alkylation is very useful for making fused ring systems. We do still have to worry about these rearrangements happening. Now there are other problems as well, in addition to the rearrangement issue that Friedel-Craft alkylation has. So let's go through those. We cannot do Friedel-Craft alkylation on an aryl halide. This is when you have a halogen directly bonded to a benzene ring, okay, like this. Or a vinylic halide. So this is an example of a vinylic halide. So the halide that we're using to react with the aromatic compound can't be a vinylic halide or an aryl halide, okay? So the halogen must be attached to an sp3 hybridized carbon. Okay, this is an sp2 hybridized carbon. This is an sp2 hybridized carbon. So here's some examples here where I've got my benzene ring. This is an aryl halide, so no reaction. And here I have a vinylic halide, no reaction, okay? So why not rip off the halogens, see what kind of a carbocation you're going to make. They're not going to be able to form stable carbocations, okay? All right, another important limitation that you need to be aware of is that the benzene ring cannot have a deactivator on it, with the exception being a halogen, and you're going to learn more about the terms, what deactivators and activators are very soon in this chapter. It also cannot have an amino group. So deactivators that you need to know about that, that you can't have on a benzene ring in a Friedelcraft alkylation include the nitro group and the sulfonic acid group. Okay, so so for example, then you have nitrobenzene. Okay, that's not going to work in Friedelcraft alkylation because it's a deactivating group. Same thing with the sulfonic acid. You also cannot have an amino group attached to the benzene ring. Why? Well, remember that our catalyst is a Lewis acid. It can accept a pair of electrons. Amino groups all have a lone pair. Is that lone pair on the nitrogen usually readily available to do? To be donated. So the amino groups will react with the aluminum trichloride, the catalyst, and destroy the catalyst. The reaction isn't going to go. So if you took one of these, let's grab this one here. Right, this is aniline, okay? And if I say, okay, I'm going to react it with our methyl chloride and our catalyst, you're going to get no reaction, okay? Because this is going to form a bond to the catalyst. All right, and then also, the news just keeps getting worse. You get in this reaction, because you are adding an alkyl group to a benzene ring, the product ends up being more reactive than benzene. And so it will go on to further react. So we get what's called polyalkylation. We end up adding many alkyl groups to the benzene ring. So for example, here in this reaction, we say, okay, we're going to end up making toluene, and you do, but it turns out that toluene is more reactive than benzene. So this is going to go on to further react with this reagent to get polyalkylation. Okay, we're going to get more alkyl groups added to the benzene ring. Well, this is problematic in the lab if you get a mixture of organic products. These are all going to be really difficult to separate from each other. Okay, so that's no good. And then I already mentioned the rearrangements, but I'll just make sure that that's officially in your list. Okay, so you get rearrangements of the carbocation. Remember that your electrophile in Friedel-Crafts alkylation is a carbocation. So you won't be able to put a nice long chain on a benzene ring using Friedel-Crafts alkylation. We've got to have something else for that, and that's what we're going to talk about in the next video. So here's an example of, we've got this 4-carbon chain. We would like to make, let's say we want to make this. Well, we're actually going to get a very low yield of this because it will rearrange to form a more stable carbocation to give us this product. So that's why Friedel-Crafts came up with another reaction called Friedel-Crafts acylation, so that they could add a nice long straight chain to a benzene ring. So that's what we'll do in the next video.